Okay, so we're going to take a look at some Verilog for finite state machines. I asked Dr. Trahan if there was anything that he thought he sensed that, could stand going over a little bit more, and he said this seemed like it was something that the students could use a little more practice with. And I'm not going to go exactly in the order that I have on the worksheet because I have, I think, 5 questions here. Yes, and 4 of them you are you're coming up with the state table or state diagram from the Verilog, and one of them you're writing the Verilog. And obviously, I think obviously, writing the Verilog is harder than reading the Verilog, and that is what you have to do in the labs. And so I thought rather than doing them in the order that I have here, we'll do all the ones where we interpret the Verilog, and then after we've done that, we'll see the patterns, and then we'll be able to go back and write it and be able to do a little better job with it. And as always, if you have any questions, please stop and ask me. And this is the Verilog for a sequential circuit. A sequential circuit Verilog is going to have 2 parts to it. It's going to have one always block where you are defining the next state. So this is the part where you're saying this is the state that comes next. And then you have another part that actually defines the sequential block that actually says, okay, now go to the next state. And so in Verilog for finite machines, you're always going to have these 2 always blocks. Do you need
Oh, yes, please, thank you.
You're welcome. So you're going to see that in all of these. And then when we look at this one, we have 4 inputs and outputs listed. We have the clock, which we would expect. We have reset in, and that's what we use to reset our finite state machine. And we have T, U, and V, and at this point we don't know because we haven't gotten into the code yet to know, actually we do know because the directions say 1 input T and 2 outputs U and V. So we know T is an input and U and V are outputs. Okay, and then as we get down a little further, we see that input is a clock. Clock is always an input. Reset in is an input. It's always an input. So when you're doing your Verilog, those are going to be inputs. And T, because here that is our input for this particular machine. And our output are U and V. Okay, so U and V are our outputs. Y, little y, and big Y are going to be our current state and our next state. And those are vectored signals. They're 2 bits wide, so they have there's 2 numbers associated with them, 2 binary numbers. And if you look at the parameter, you can see that there are some examples of some 2-bit binary numbers right there. And on the parameter, we're using that just to define D, E, and F so that we don't have to write 2'B00 every time. We can just use D. So that's just like using a state table, just using the letters instead of putting in the binary numbers. So that's what the parameter is for. And the 1:0 means that it's 2 bits wide. It's made up of 2 bits. So our states are 2 bits. They can be 0, 0, 0, 1, 1, 1, and then there is a don't care state of DD that we don't have to worry about here. Okay. All right. So now we get to our always block, and the always block says always at T or Y. So it's going to do what's in this always block whenever there's a change in either T, which is the input, or Y, which is the state. And so it's going to look at Y, and then depending on what Y is, it's going to do something. Now you'll notice that our output is not defined until we're outside of this always block. That means our output does not depend on our input. And so what kind of machine does that make this? Mealy or Moore? More, yeah. I always forget, but actually I did know this time. For whatever reason, I can't ever keep those straight. Okay, so we see that we've got our three states here, and we're supposed to come up with a state table. Yes, I'm going to do a state diagram first because those are easier, at least for me. So we have our three states, D, E, and F. And if we are in state D, and T, the input, it says if T. That means if T equals 1. So if T equals 1, then Y equals D. Now, we're not using the non-blocking assignment. Notice if you look down at this next always block, we're using the non-blocking assignment because we want that when we're actually changing the states. By non-blocking, I mean the little less than with the equal sign. And what this does is it fixes the states at the beginning of the always block, and it doesn't, like if you change one state, it doesn't use that new value of the state. It just fixes them from when you enter into the always block. But we don't need to do that here because this is not at the positive edge of the clock. This is all the stuff that's going on until we get to the positive edge of the clock. So if T is 1, if we're at D, so that's what a case statement says. If we're at D and T is 1, then our next state is D. So we're going to go back to D, and this is if T equals 1. Else, Y equals F. That means our next state is F. So we'll go here, and that would be if T equals 0. Okay, so we've taken care of D. Now, if we are at state E, then if T equals 1, then Y equals E, so we go back to where we started. Else, that would mean T equals 0, then we go back to state D. Okay, now we're at our last case, F. If T equals 1, then Y equals E, so here we'll have T equals 1. Else Y equals F, so here F is going to go back onto itself if T equals 0. And then anytime you have a case statement, you have to have a default, especially here it's important because we don't have something defined for all 4 possibilities for 2 bits. And so we really need to have a default there since we don't have 0, 0, 0, 1, 1, 0, and 1, 1. But you should always have a default anyway. Okay, so what this default is saying is that if you did happen to get a 1, 0, which is not D, E, or F, then the next state would be D. Okay, so that is defining the next state. Before I go on, let me see if that matches what I have here. And it does. Okay, and now we get to the sequential block, and the sequential block is at either the negative edge of reset in, that means you pressed the reset in button, or the positive edge of the clock. So if reset in equals 0, that's the same as saying if not reset in, that actually means you want to reset. Reset in always gets me a little confused, but if reset in equals 0, then you want to reset, and reset means that Y equals D. So reset is here. So reset goes to D. Else, little y becomes the big Y that you calculated up in the always block above. Okay, so now we're going to define the output. The output depends just on the state, so that makes it a Moore machine. And we're saying U is equal to Y equals E. That's the same thing as saying U equals 1 if y, so I'm not going to use the programming equals here. U equals 1 if y equals e, and u equals 0 if y does not equal e. So u equals y equals e. Y equals e is a conditional. It's saying, what that is saying is, evaluate, does y equal e? And if y equals e, then that statement is true and it's a 1. And if y does not equal e, then that statement is false and it's a 0. So here, u is going to equal 1 if y equals e and 0 if y does not equal e. So u, how did I write this on here? I just put u. So u equals 1 for state e, and u equals 0 for D or F. And then V is equal to y equals D or y equals E. So if either of those two things is true, then V is 1. So that means if y equals D, then V is 1. Or if y equals E, then V is 1. And otherwise V is 0. So V equals 1 here. And V equals 1 here. And V equals 0 here. Okay, now this particular question asked for a state table, not a state diagram. So now we need to draw a state table. Should probably stick to the straight line tool because I have tremors as it is and no sleep and can't draw straight lines in the best of times. So although this is about as good as it gets for me. Okay, so we have present state here. And then we'll have our next state. And next state if t equals 0 or if t equals 1. And then our output, u and v. And our three states are D, E, and F. And so D, go back and look at our state diagram. When t was 0, we went to F. When t was 1, we went back to D. Our output was u is 0 and v is 1. For E, when t was 0, we went to D. When t was 1, we went back to E. And our output was u was 1, v is 1. And for F, when t was 0, we went back to F. And when t was 1, we went to E. And our output was 0, 0. Let me see if that matches what I have here. My handwriting was much neater this morning. And that looks like the same that I have here. So I'll get back to that in just a second.